Here is a problem from Chapter 7 of Neamen having to do with a junction between two materials which have different doping. Let me give you some time to read through the problem and try it out yourself. Do try to do it as much as possible before continuing with the video where we'll work it out together. This problem has a junction between two different materials, but what is unusual is that they're both N-type. So it's sort of like a p-n junction, except with two N-types with different dopings being put into contact. And you can see the exact concentrations are given in this figure here. So what we're going to do is work on parts A and B. Those two sort of go together. A is sketch the thermal equilibrium energy band diagram, and then part B is, using that, determine the built-in potential barrier. So just to be clear what we're talking about, we have a junction between two materials. I'm calling this side the left side and this side the right side. They're both N-type, so this is N and this is N. And this has a doping, I'm going to call it ND left, and this has a doping NDR for right. And those are the same as on this diagram. This will be ND left, and this will be ND right. Basically what we're after from all the way through part B is our goal is to find the built-in potential VBI. So the wrong way to approach the problem would of course be to go to the equation sheet. You might find this equation, VBI equals KBT over E natural log of ND NA over NI squared, but that doesn't work obviously because there's no NA, right? There's no acceptors in this problem. So this problem's not going to work, or this formula is not going to work. So we need to think a little bit harder about how to approach this problem. The correct approach to the problem is hinted to in part A. We're going to use energy band diagrams. And you have to remember a couple things. The two most important things to remember are that doping changes the position of EF. We know that for N-type material, EF goes up. Fermi energy is increased as the doping goes up. And then the other key point to remember is that in equilibrium, EF is constant throughout the material. So those are the key points. There's different dopings on each side. So that means the Fermi energy is in different spots initially. Then when the things are put into equilibrium, when these two materials are put in contact and it forms equilibrium, EF has to become a constant. And as a result, the other bands, the conduction, the valence band, and EFI, need to bend. And that's where we get our built-in potential. So our plan is to do the same derivation that we did for the p-n junction, is draw the energy bands for each side separately. And EF will be in a different position. Then when you put them in contact, we're going to shift one of these set of diagrams. so that EF on the left side equals EF on the right side. And finally, the amount of that shift is going to be equal to E times VBI. Not exactly VBI because one is an energy shift, one is a potential energy, but they're very closely related. So however much I have to shift them so that they are so that the Fermi energy is the same on both sides, that's the height of the potential hill that will develop. And of course, this amount of this shift will be equal to the initial difference EF left minus EF right. Okay. So that's the plan. Now we can go ahead and start executing it. So that's the plan. We're going to go through this derivation. And usually we draw two diagrams. So first I'm going to draw the energy level diagrams before anything happens. So that's before the two are even in contact with each other. I'll draw the energy level diagram on the left and on the right. So we'll say this is EFI, EV, EC, and then similar diagram on the left, EC, EFI, EV. And then where is the Fermi energy? They're both n-type, so the Fermi energy is going to be above EFI. Let's call this EF on the left. And then here, this will be EF on the right. Notice I put them at different levels because the doping is different on each side. Okay? So the more doping I do, the higher up the Fermi energy is. There's a higher Fermi energy on the left side than on the right side. And as I mentioned in the previous slide, when they are put in contact, we have to shift the energy bands so that the Fermi energies line up, so that they're the same all the way across. And the amount that we have to shift it is exactly this much here. This is going to be EF left minus EF right. This is the size of the shift needed to make those two Fermi energies line up. And that is exactly going to be my built-in potential, EF left minus EF right. There's a factor of E that relates those two, just because one of them is electric potential, one of them is energy. Okay, so that's before contact. Let me draw it again now. When they put into contact, I'm just going to take this same diagram. I'm going to shift the right side upward so that everything lines up. So that's what it looks like. I've shifted the graph on the right upwards so that that blue line, the Fermi energy, lines up between the two sides. And then we connect everything with a smooth curve. The conduction band throughout the whole material is connected. The valence band throughout the whole material is connected, and EFI is connected. And we have a bending of the bands from one side to the other. All the other bands bend so that the Fermi energy is the same throughout the material. And how high is this hill? This built-in potential here, which we call EVBI, well, that is exactly the amount that we had to shift it upwards. It's exactly the height of the original shift, or the height of the original difference between the Fermi energy on the left and the right. Okay, so all of this is a graphical representation showing you what I had claimed previously, that the built-in potential is just the initial difference between the Fermi energies. Okay, so now we have the main idea. We just have to figure out this initial difference, and that can be used to determine VBI. So we need to do a little bit more planning now. We need to relate the position of the Fermi energy EFL and EFR to the doping, Nd on the left and Nd on the right. And then we need to determine EFL minus EFR. And that will be equal to the answer to part B, which is E times VBI. How do we relate those two? Well, we know that there's the main equation relating doping and Fermi energy. So, NC e to the minus EC minus EF over KBT. And we know they're both n-type, and we're going to assume they're strongly n-type. So N0 is approximately equal to ND. So I've got one equation on the left, which is ND on the left is NC e to the minus EC minus EF on the left over KBT. And then one equation for the right, which is like this. Looks the same. Over KBT. So now we have those two equations, so we can try to plan out the steps. Let's call this equation 1, this equation 2. We're going to solve number 1 for EF left, and we'll solve number 2 for EF right, and then we'll subtract them. And we'll get EF left minus EF right, and that'll be our answer. So now we can just execute this plan. Okay, so let's try to do these steps efficiently. So first thing I'm going to do is divide by the NC, so ND left over NC is equal to E to the minus EC minus EF left over KBT. Then I'll take the natural log of both sides. So there you have it. And finally, I have to do a little bit of algebra to solve for EF left. So I think that's what it looks like. And then now we'll do the same thing for the second one, which we can do quickly because it's the same equation just with different letters. I just have to change, everywhere I have an L, I change to R. So I get another equation which looks like this. There you go. And now, according to our plan, the next thing we should do is subtract those two equations. So I'm going to subtract them. On the left side, I've got these two natural log terms, and then I've got these ECs, but the ECs are going to cancel when I subtract. So what I'm going to have is the following. Just like that. Now, in some sense, you might be thinking you're stuck here because we've got NC, and I don't really have any information on the material, so it seems pretty tricky, but I can do some algebra. I can combine those two logs together using the rule natural log of A minus natural log of B is equal to the natural log of A over B. I can combine those two together, and you'll see things will simplify. So that's what it looks like. I pulled out the common factor of KT, and then I combined the two logs together. I have ND left over NC divided by ND right over NC. And so the NC's cancel, and I have this nice final formula here, which looks like this. So in fact, everything canceled out here except for the temperature and the two doping concentrations. And that tells me the built-in potential. So there we have our final formula. Now we just have to plug numbers in. Let's assume it's at room temperature. It's not given in the problem, so we'll assume the usual thing and plug in the numbers. At room temperature, kBt is as usual 0.026 eV. And then nd left over nd right, it's easy enough, 10 to the 16 over 10 to the 15 centimeters to the minus 3 centimeters to the minus 3. The units on the left are on the top and the bottom are the same. So what's inside of the natural log has no units, which is as it should be. So I get 0.026 eV natural log of 10 is going to be equal to E times VBI. And then we can do this thing that I like to do, which is just to cancel out the E's. The E on the left and the E on the right cancel out. So I have something left which is just in units of volts. So VBI 0.026 times the natural log of 10. Whole thing has units of volts. I get 0.599 volts for VBI. So that's a nice problem, parts A and B. It really requires some conceptual work because there's no formula. We never derived in class the formula for the built-in potential between two n-type materials. The steps are exactly the same as a p-n junction. We ended up with a different formula which you hadn't seen before. Check the units, and this is what we get. So that's the answer to part B. Now that we have a numerical answer, let's spend a minute making sure that it makes sense. We've already checked that the units work, so there's no problem there. The other thing you can check is that anytime you derive an algebraic formula, so we have this nice algebraic formula here, which is true for any problem of this type with these two different dopings, you can check your formula in special cases. So for example, I could imagine, what if nd left was equal to nd right? That's not the case for this particular problem, but because I have a formula which is true for any problem like this, I could make sure that the answer that I get from this formula works. If nd left is equal to nd right, then there's no junction, because the material is the same on both sides, and I should expect VBI equals to 0. Let's check it. Use the formula, kBt. This is E times VBI. Natural log, if nd left is equal to nd right, inside of the natural log is 1, and the natural log of 1 is 0, and so makes sense, right? Finally, you can check, is the value reasonable? That's a little harder to get intuition for. In this case, my VBI is approximately equal to 0.6 volts. And generally, this is something that you would have to develop this intuition by doing more problems having to do with built-in potentials. But VBI is usually between 0 to 10 volts, roughly. It's never 100,000, it's never a million volts. If you ended up with a really, really huge VBI or a really, really tiny VBI, that would give you some pause. But in this case, 0.6 volts, between 0 and 10 roughly, seems like it's in the ballpark, so that's reasonable. So our answer meets all of these checks, the special cases, reasonable number, and the units, so we have confidence that this is in fact the right answer, and we've finished the problem. I won't work out part C, so I'll leave that as an exercise. But it's interesting to think about where the charges are in this NN junction. So I'll let you guys think about that to yourselves, and I'll just stop the video here, having completed parts A and B.